Welcome, curious minds, to the deep dive. We're zeroing in today on, well, one of humanity's really big challenges, climate change. And while, we're all working on cutting emissions, there's also this fascinating area of innovation happening. Some ideas sound almost like science fiction.
Absolutely. And one of those ideas, one that's gotten people talking for a while now, is stratospheric aerosol injection. You might hear it called SAI.
SAI, right.
Basically, it's this concept aimed at counteracting global warming. The idea is to reflect some sunlight back into space, kind of like giving the Earth a very, very subtle shield.
But the early thinking on SAI always seemed to come with these pretty significant side effects, didn't it? That was always the sticking point. Promising, maybe, but also risky.
Exactly. That's been the core question all along. Can we actually use this powerful idea without, accidentally creating a whole bunch of new problems?
And that is precisely what some really fascinating new research is digging into. So today, our deep dive is exploring this paper, Injection Near the Stratopause, minimizes the stratospheric side effects of sulfur-based climate intervention by UN colleagues. Our mission here is to unpack this novel approach to SAI they propose, one that promises to seriously cut down those side effects, and, well, what that might actually mean for us.
Okay, so at its heart, stratospheric aerosol injection, or SAI, is conceptually pretty straightforward. Imagine injecting tiny sulfur particles way up high into the stratosphere. That's the layer well above where commercial planes fly.
Right.
These particles would then form this kind of reflective layer, scattering some of the sun's heat back out before it warms the surface.
Much like what we see happen naturally after a huge volcanic eruption, right? Like Pinatubo back in the 90s, the Earth cooled off for a bit.
Exactly like that.
Yeah.
And the motivation is clear. We want to try and keep the planet from warming past those critical thresholds scientists talk about, like 1.5 or 2 degrees Celsius above pre-industrial levels. It's seen as a potential way to maybe buy us some time.
But the challenge, as you mentioned, has been with let's call it the traditional way people thought about doing this. Most of the research looked at injecting sulfur much lower down, maybe around 20 or 25 kilometers. We can call that SAI 25.
Yeah, SAI 25. And while models showed it could cool the planet, it also came with, well, some pretty serious hidden costs.
Okay, those hidden costs, that's the crux of it. When scientists modeled SAI 25, what were the big environmental trade-offs they found? Why were people so concerned?
Well, one really significant side effect was something called tropical lower stratospheric warming. Basically, SII 25 looked like it would cause substantial warming around 6 Kelvin, 6 degrees Celsius, in that specific part of the atmosphere, the lower stratosphere over the tropics.
6 Kelvin? Okay, that sounds like a big number for up there. How big a deal is that, warming the stratosphere by 6 degrees?
It is a big deal. I mean, while you wouldn't feel it directly down here, a 6 Kelvin shift in that specific layer is a major change atmospherically. It has knock-on effects.
Like what?
For instance, that warming leads to a big increase in stratospheric water vapor. We're talking about 340 teragrams, roughly a 15% jump.
And water vapor up there is a greenhouse gas too, isn't it?
Exactly. So it actually cancels out some of the cooling you're trying to achieve. Plus, this warming could mess with atmospheric circulation, strengthening the polar jets, weakening the subtropical ones, potentially shifting weather patterns down here.
So you try to fix the warming, and you end up potentially scrambling weather systems. Not ideal. What was the other major worry?
The second big one was about the ozone layer. Specifically, it looked like SAI 25 could significantly delay the recovery of the Antarctic ozone hole, getting back to those 1980s levels, around 290 Dobson units. The delay was estimated at something like 25 to 55 years.
Wow. And just remind us quickly, the ozone layer, that's crucial because
it shields us.
Yeah.
Protects all life on Earth from harmful UV radiation from the sun.
Right. And why was injecting lower down this SAI 25 causing such a problem for ozone recovery?
It's about the chemistry. Those sulfide particles injected into the lower stratosphere provide surfaces, like little platforms, for chemical reactions to happen. And unfortunately, these reactions release chemicals that destroy ozone, particularly bad in the cold polar regions. So it basically slows down the healing process that's already happening thanks to things like the Montreal Protocol.
Okay, so messing with weather patterns, delaying ozone recovery by decades. It sounds like SAI 25 had some, near deal-breaking problems.
Pretty serious drawbacks, yeah.
But this is where it gets really interesting. This new research proposes something quite different. SAI 50, they call it. Injecting the SO2 way higher, near the stratopause, around 50 kilometers up.
Exactly. And that higher altitude, it turns out, is absolutely key. It uses a different part of the atmosphere's natural transport system. Up at 50 kilometers, there's this circulation pattern. the mean meridional overturning circulation, that works much faster. It basically whisks the aerosols away from the tropics and moves them towards the mid and high latitudes pretty quickly.
Like an atmospheric conveyor belt?
Sort of, yeah.
Yeah.
A slow-moving one, but effective. It stops the aerosols from building up in that sensitive tropical lower stratosphere where they cause the warming and water vapor problems. And just to be clear, you inject SO2 gas up at 50 kilometers, but it forms the actual sulfate aerosols as it travels down and poleward, mostly ending up around 10 to 30 kilometers altitude in the mid to high latitudes.
Got it. So it's not just higher, it's about where it goes after injection. So what are the benefits then? How does this SAI-50 stack up against the old SAI-25 approach? Because the improvements sound, frankly, pretty dramatic.
They really are quite remarkable. First off, that big tropical lower stratospheric warming, the 6 Kelvin problem.
Yeah.
With SAI-50, it's cut by more than half, down to just 3 Kelvin.
Yeah.
And that means the increase in stratospheric water vapor is also way smaller. Only about 90 teragrams, maybe a 4% increase compared to that 15% jump with SAI-25. And the effects on the jet streams also significantly reduced.
Okay, that's huge for reducing those side effects. But does it still actually cool the planet effectively? You're putting it so much higher up.
Get this, it not only cools effectively, it actually provides more cooling.
Really?
Yeah. SAI-50 shows about 22% more global average surface cooling compared to SAI-25. And even more impressively, 40% greater cooling at the poles. That's an extra 1 to 3 degrees of cooling right where we need it most.
40% more at the poles. How does it manage that?
Well, it does this, even though the overall amount of aerosol globally, what we call aerosol optical depth or AOD, only increases by about 10%. It seems to be because the aerosols end up distributed more effectively in those mid to high latitudes, and you get that amplified cooling effect in the Arctic.
That's incredible. More cooling, fewer side effects. So what does that mean for something tangible, something you can picture, like sea ice?
Right, for you, this translates into much better sea ice preservation. Under SAI-50, the models show it preserving about 20% more Arctic sea ice in September. It reaches about 56% of its March maximum extent, whereas SAI-25 only got it to 36%.
Big difference. What about the Antarctic?
Even more striking there, actually. Sea ice extent down south increases by 1 to 2 million square kilometers compared to SAI-25. That's like a 100% relative increase, a really significant boost for Antarctic sea ice.
Okay, so better cooling, especially at the poles, much better for sea ice. What about the ozone layer? That was the other huge stumbling block for SAI-25.
This might be the most dramatic improvement of all. Remember that frightening 25 to 55-year delay in Antarctic ozone recovery with SAI-25?
Yeah, hard to forget.
With SAI-50, that delay is slashed to only around 5 years.
5 years. Down from potentially 55. How?
It's because the aerosols end up accumulating more in the middle stratosphere, maybe around 25 kilometers, but at high latitudes. And in that region, they lead to more depletion of nitrogen oxides.
NOx.
And oxys. Those are bad for ozone. Generally, yes, in that part of the stratosphere, no-NOx compounds catalytically destroy ozone. So by reducing NOx up there, SAI-50 actually removes one of the things hindering ozone recovery. In fact, the research suggests that looking forward, under certain future conditions, SAI-50 might lead to practically no reduction in total ozone compared to a world without any SAI at all.
That's revolutionary, really. Shifting the injection height makes that much difference.
It seems to fundamentally change the balance of side effects versus benefits.
Okay, but this does raise a pretty major question. If 50 kilometers is the magic altitude, how on earth do we get potentially millions of tons of sulfur dioxide up there every year? Normal planes can't fly that high.
No, they definitely can't. And that's the huge engineering challenge, which the paper does address head on. The proposed solution involves using a fleet of reusable rockets.
Reusable rockets, like space launch technology.
Essentially, yes. Flying suborbital trajectories, so up and then back down, delivering their payload near the peak.
Okay. What about the pollution from the rockets themselves? Are we creating one problem for another?
That's a critical point. The researchers strongly recommend using hydrogen-oxygen propellants. The main emission from those is just water vapor, which they calculate would have negligible impact on climate or ozone. That's way better than, say, kerosene-based fuels, which have more complex emissions.
Clean rockets, got it. What kind of scale are we talking about here? How many rockets? How often?
Well, to hit that 1.5 degree sea temperature target, the estimates for the period 2040-2060 are injecting maybe 3 to 8 teragrams. That's millions of tons of SO2 per year.
Okay.
To do that, you might need a fleet of, say, 30 to 80 very large reusable rockets. Think maybe 500-ton payload capacity each. and they need to be launching very frequently, perhaps one launch every other day, system-wide.
Wow, 30 to 80 giant reusable, clean-fueled rockets launching almost daily. That's a massive undertaking.
It is, absolutely. But the paper argues it's within the realm of, let's say, foreseeable technology. There's even overlap with concepts being explored for rapid point-to-point cargo delivery using rockets. The detailed engineering isn't done, obviously, but it's not considered science fiction anymore.
Still, it's a huge logistical and presumably economic challenge, and it's important, I think, to keep a balanced view. While SAI 50 seems to drastically cut down some of the biggest worries about SAI, it doesn't make all the challenges disappear, right? There are still fundamental issues with any SAI approach.
Absolutely right. You have to maintain perspective. For instance, there's the whole issue of termination shock.
What's that?
It's the risk of rapid warming if you were to suddenly stop the injections after decades of relying on them. SAI isn't a one-off fix. It requires a multi-decade, maybe even century-long commitment. Stopping abruptly could cause the climate to warm very quickly to where it would have been without SAI.
So it's a long-term commitment with potentially severe consequences if you stop. What else? Are there things we still just don't know?
Definitely. There are still uncertainties in the climate models, especially when it comes to predicting precise regional changes like rainfall patterns. And understanding the really long-term impacts, like on deep ocean circulation, would require simulations running for many centuries. So there are still knowledge gaps.
What an incredible deep dive this has been. We've gone from the initial concept of SAI, with its really concerning side effects like stratospheric warming and major ozone delays.
Right, the SAI 25 problems.
To this new research showing how simply changing the injection altitude going way up to 50 kilometers could dramatically slash those side effects and actually boost the cooling power, especially for the poles and sea ice. And the ozone recovery issue almost vanishes.
It really does seem to reshape the potential, doesn't it? This SAI 50 approach offers a pathway that looks significantly more effective and, crucially, much less disruptive to the stratosphere than what we were looking at before.
So, the final thought for you listening, what does this all mean? We have this potential tool, SAI 50, that looks much, much better on paper for tackling warming and protecting the ozone layer. But deploying it involves this, well, monumental engineering fleets of reusable rockets flying constantly. How do you weigh those huge implementation challenges against the escalating risk of not doing enough about climate change? And what kind of new ethical or societal questions does a technology on this scale even raise for us? It's definitely a lot to think about.